Next up, we're going to talk about how to take Laplace of periodic functions. And we are going to have to return to thinking about that integral definition of a Laplace transform, but I promise it's not going to be that super complicated infinite integral thing. It's just sort of a neat trick that we can take periodic functions and only integrate over a finite space. So, if f of t is a periodic function, and if its period is given by capital T, then the Laplace transform of f is going to look like an integral, like how we define Laplace transforms when we're calculating them manually. It's going to be 1 over 1 minus e to minus s times capital T, that period. And then we evaluate our integral from 0 to capital T, that period. And we look at e to minus s times little t, f of little t, integrated against time. And this is just a formula that we can use to compute Laplace of periodic functions. So we're going to go ahead and experience it through an example. We're going to compute L of a function little e for e given by this graph. And what it's going to be is that over time, e is going to jump between 1 for 1 unit time and then stay down at 0. Then go up at 1 for 1 unit time and go back down to 0. And it's just going to keep doing that over and over. And so when we're looking at this, periodic means it repeats. So we can see it's up, down, up. It is repeating. And the period is sort of the shortest possible time you would need to look at it before you could copy paste and get all the things it's repeating. So for us, we need this up period and we need this this up duration and down duration. So the period would be from 0 to 2. So it's periodic with period t equal 2 for that capital T. And so just to write out, the behavior of E is that it has period 2. And then for, I'm going to go ahead and write period t equals 2. And then for any duration of time inside that period, I'll go ahead and do inclusive. One of these little snapshots of it, or copies of the periodic part, I'm going to denote by E tilde, and all it does is it starts at 1 and it goes to 0. And it's 1 from 0 until 1, and then it's 0 after 1 until 2. The equal on the less than signs isn't super important here because we're going to be thinking about integrating it. An integral actually doesn't care about value at a discrete point, so you could like swap this and it would be the same thing. But I've decided to write it this way. So, if we want to compute Laplace transform of E, we're going to have to use this formula, 1 over 1 minus e to minus st, evaluating the integral from 0 to t of e to minus s times little t, times whatever our function takes on within the integral, and so that's that e tilde that I just wrote down. And and we'll integrate that with respect to t. And what I'm going to end up doing is moving to the next slide to write out the integral where we plug everything in. So do pause if you're still working here. But for us, our period was 2. So 1 minus e to minus st is 1 over 1 minus e to minus 2 times s for capital T equals 2. And our integral from 0 to capital T is actually 0 to 2. And then we've got that e to minus st times e tilde of t dt. And then to write e tilde, it's a piecewise function. It's all your favorite type of function to write down an integral of. We are going to have to break this up into 2 parts. So we're going to have 1 over 1 minus e to minus 2s times whatever happens from 0 to 1 plus whatever happens from 1 to 2. And e to minus st stays the same. I'm still integrating with respect to t. And then I just have to plug in the different values that happen between 0, 1 versus 0, 2, or 1, 2. So from 0 to 1, we said that the function has value 1. It's the high part. And then from 1 to 2, the function has value 0. It's the low part. And so the second integral that we wrote down actually just goes away because it's 0. And so we're going to have 1 over 1 minus e to minus 2s, the integral from 0 to 1 of e to minus st times 1, which we can stop writing that in dt. So now we have, I think, a really simple integral that we just have to evaluate. 1 over 1 minus e to minus 2s. The only tricky part is that we're integrating with respect to t, so we remember that minus s we treat like a number. If you integrate e to 2t, you would get like 1/2 e to 2t. So when I integrate e to minus st, I get 1 over minus s times e to minus st, and I evaluate that from 0 to 1. That's going to give me 1 over 1 minus e to minus 2s times, let's see, e to minus s plugging in t equals 1 divided by that minus s minus e to minus s times plugging in t equals 0 divided by that minus s. Or just kind of cleaning this all up so it looks nicer, I can pull out that 1 over s. I note that everything is divided by 1 minus e to minus 2s. Then this minus minus becomes a plus, and this one stays minus. E to 0 is 1 minus e to minus s. Just showing that to you kind of in more steps. That's 1 over s, 1 over 1 minus e to minus 2s, and I'm left with e to minus s negative plus e to 1. And then I just swapped their order because, sorry, e to 0. And then I just swapped their order because I like having the 1 and the 1 lined up like that. That's not as good as I hoped it would be. So, hopefully you can see that this is a pretty straightforward process. Once you identify t, you set up your integrals and then just evaluate them. And it's easier than when we had those infinite integrals that we were thinking about for the first definition of the Laplace transform. The only thing that I would say to be careful about is that you do have to remember to plug those integral bounds into values t, not values s. So since we're taking a Laplace transform, we know that all t should go away and I should only have s left over. When you're integrating, it's easy to forget that. So just be careful of what you're integrating with respect to, and you should be okay for this type of problem. So I'm going to pause here before moving on to our last video, which is kind of trying to tie all of our Laplace transform stuff together.